Hi everyone, in this video we are going to discuss a few aspects of some of the reducing agents in organic chemistry. So to begin with, let us take up sodium borohydride, which is also called as NaBH4. So when we look at NaBH4, it's actually Na plus and it's BH4 minus. So because of this boron carrying negative charge, this can actually act as a H minus donor. So basically the reducing effect is caused by H minus. So it's a nucleophilic reducing agent. So wherever you see the reaction of NaBH4, it's due to reaction of H minus, which is going to be a nucleophilic reaction. And we see the preparation of sodium borohydride is like NaH, that is sodium hydride, is treated with trimethoxyboride. So this on reaction at around 200 degree, that's something like 470 to 500 Kelvin, gives NaBH4, and we get sodium methoxide. So in order to balance, we will have to write it is 4 NaH and here it is 3. So in this way we get NaBH4 prepared in the laboratory. It's a very important reducing agent. It's a very selective reducing agent. It is very selective reducing agent. So what is the meaning of selectivity? So it does not affect many of the functional groups, though it is very conveniently used for reducing aldehydes and ketones. So it does not affect carboxylic acid, then it will not affect ester, then it will also not affect double bond and triple bond, then it will also not affect CN, that is nitriles, then it will not affect even NO2, ether, then it will not affect NO, and it will also not affect, it's not very effective with, not effective for primary alkyl halides also. So these are actually even epoxide. So I can write here epoxide, basically cyclic ether. So all these groups are not affected by NaBH4. Now let us understand how exactly the reduction takes place and where does this NaBH4 stand. Suppose we compare this with reputed reducing agents. So like LiAlH4 will be the most effective, most reactive. Then it's followed by LiBH4, then NaBH4. See, this, the difference, the reactivity of BH4 minus and ALH4 minus are different because electronegativity of boron and aluminum is also different. The anion is more stabilized with boron. The negative charge is actually more stable on boron than aluminum. So as a consequence, BH4 minus will be a stable anion compared to ALH4 minus. ALH4 minus being extremely unstable will always fire H minus very quickly, and that H minus will be very reactive obviously because it is coming out of a reactive species. So once we understand the position of NaBH4, let us also understand the mechanism, in what way it will actually affect the substrate. So let us write mechanism here. Say mechanism. So best compound to discuss mechanism is actually aldehyde or ketone, because that's where we see NaBH4 active and doing a good job. So RC double bond H in presence of NaBH4. So basically NaBH4 gives H minus. So this H minus will attack this carbon and it will cause shifting of bond like this. Then naturally this will become R, C, O minus, and this is going to have H now, which is actually from sodium borohydride. So one more H already present in the compound. So this one on hydrolysis yield R, C, O, H, H, H. So basically it is converting a aldehyde into a primary alcohol. Primary ROH or primary alcohol. So similarly, it has its own set of reactions with different reagents. Generally, the solvent which we use with sodium borohydride is alcohol, methanol or ethanol, because obviously this should not be taken in aqueous medium. Sometimes it can be given also, but unlike lithium aluminum hydride, this won't require aprotic solvent. It's not so reactive, because lithium aluminum hydride requires aprotic solvent like ether, THF. So those are the reagents which we generally use. So now just to give a comparative analysis, so here we can see that this LiAlH4, I mean sodium borohydride, will convert aldehyde RCHO to RCH2OH. So we already saw the mechanism. So similar mechanism is seen for even R2CO. So this is a ketone. So this ketone is converted to RCHOHR, which is actually secondary alcohol, and here you have primary alcohol. Then we also know that R2, instead of R2, let us take it as R, C double bond OCl. So acid halides are going to be converted to RCH2OH. So this is also very interesting reaction. So it converts the acid halide to conveniently alcohol without any other support of reagent or something. And there is also one more important use which is not dealt in most of the textbooks, is that its ability to reduce olefinic ozonide. Olefinic ozonide is converted to alcohols, and this is again is a reduction process. Then we also see that it can reduce RCH double bond NH to RCH2NH2. This is also, I found it in a book, that if it is imine, it will actually reduce it to amine, but it will not affect carbon, like nitrile, RC triple bond N. That will not be affected by the NaBH4. Then it can also reduce, so let us see that secondary and tertiary RX2 conveniently alkane, RH. So secondary and tertiary RX are conveniently converted to alkanes. Then another important application which is not again dealt in most of the textbook is its ability to reduce benzene diazonium salt like this to benzene. So this will also occur in presence of NaBH4. This is also possible. Apart from all this, there is one more reaction, that is ester. So we see that this NaBH4 can also reduce ester to alcohol, but that requires the presence of Lewis acid like lithium chloride. So we have RC double bond O, OR1 in presence of LiCl and diglime. Diglime is an ether, it's a type of ether, and in this particular condition, NaBH4, so NaBH4 can convert ester to RCH2OH and R1OH. So basically, we are able to see that in presence of lithium chloride, NaBH4 is reducing ester to alcohol also, but this is not possible otherwise. So NaBH4 can effectively reduce aldehyde, ketone and acid halide, especially acid chloride, to alcohol, and it is also useful in reducing secondary and tertiary RX, that is alkyl halide, to alkane. So it's going to be alkane here. So these are some of the important reactions shown by NaBH4. So in next section, let us look at one or two questions wherein NaBH4 is acting as a reducing agent. So here, in the first question, if you see, there is a functional group. There are three functional groups, in fact. So one is nitro group, another one is CHO, and another one is ester. So only NaBH4 is mentioned. Sometimes along with NaBH4, even if it is methanol or ethanol, we don't have to think second time. We don't have to react the ester group. So here NO2 is not affected and ester is also not affected. So what product you get is only COOCH3, and here it's going to be NO2, and here it is going to be CH2OH. So this will be the product. Very simple. Now here, the first NaBH4 will not affect the double bond, and it will selectively reduce ketone to secondary alcohol. Once we get secondary alcohol, then there is concentrated H2SO4, which is going to perform elimination reaction. So it's a conjugated alcohol. I mean, there is a possibility of conjugation for the carbocation formed here. So this is going to be the carbocation intermediate, which is going to be the intermediate here. Now, there are two possible cases now. First one is that this double bond can shift here and have positive charge over this. So in that way, this will be the carbocation. And another one is this itself. If you look at these two structures, both are equally stable actually, and the final product will be anyway elimination product only. So it will be conjugated diene like this. So this will be the product, because both the carbocations here are equally stable. There the product will be this only. So this is how NaBH4 can be used to construct very good questions in the competitive exam. So in our next section, we are going to discuss DIBALH, or it's also called as diisobutyl aluminum hydride. So let us look at its structure and its preparation, and also its application in reduction reactions. So structure, if you look at, and there is one more isobutyl group like this. So 1, 2, 3, 4. This is isobutyl group. So this is the structure of DIBALH. Should be 2 diisobutyl aluminum hydride. Now the preparation. When we look at the preparation, it's not very difficult. So we use triisobutyl aluminum, which generally exists as a dimer. This exists as a dimer because aluminum has a lack of octet, electron deficient compound. So this on heating will undergo disproportionation and it will form IBU2ALH, which is our DIBALH. And it will also form alkene. The alkene is this alkene. So 2 moles of this will be formed. So if we look at the reaction, I think it's going to be 2 moles here also. So this is the preparation method, the simplest method. There are many other ways of getting the isobutyl aluminum hydride. So let us look at its reaction. If we notice this aluminum hydride, diisobutyl aluminum hydride is electrophilic in nature. It's not satisfied with respect to the octet. So this is a electron deficient species only. So it is going to act as Lewis acid. So you can say electrophilic in nature. So we have electrophilicity of aluminum acting. So it is electrophilic in nature, and it performs reducing reaction, causes reduction. So let us see how exactly it does in some of the mechanisms. So looking at the selectivity, it's also very selective. It does not affect. It's an important point. So we should know. Does not affect. C double bond C, C triple bond C, and it will also not affect any of the alkyl halide. Then it will not affect ethers, and it will not affect also nitro group, and it will not affect nitroso group, and it will also not affect alcohols. Like there are some compounds which reduce alcohol also, like we have red phosphorus in HI. So these are all not affected by the DIBALH or diisobutyl aluminum hydride. So let us see what are the groups which actually are affected by this. The groups which are going to be affected by this DIBALH. So DIBALH conveniently reduces ester actually, RCOOR dash. So ester is conveniently reduced to aldehyde and alcohol, and it will also reduce nitriles, RCN to RCHO and ammonia. And one more very important application of this DIBALH is alpha beta unsaturated carbonyls, allyl alcohols. It converts them to allyl alcohols. And there is also one more reaction which is not generally touched by any of the books, that is conversion of carboxylic acid, RCOH to alcohol. This requires actually extreme conditions, and it's not very good at this reaction. So at our NCERT level and whatever JEE means advanced NEET level, we don't encounter reaction of carboxylic acid with the DIBALH. So we don't have to consider that to such an extent. So it's okay to leave this conversion. So let us see some more variations possible with DIBALH. Another important conversion which it does is also conversion of RCN to RCH2 and H2. Generally this conversion is done only by H2PT, then lithium aluminum hydride, but this DIBALH also can do this. Basically we see that the nitriles get converted to RCH2 and H2, that is primary amine, when we have two equivalents of DIBALH. And generally it occurs at room temperature. The temperature is room temperature here. Now in all other cases, like here it's one equivalent, so let me make note of that. It is one equivalent here, one equivalent, and low temperature, so low temperature. and this is also low temperature, and it's 2 equivalent. So here you require 2 equivalent low temperature, and carboxylic acid converting into alcohol requires 3 equivalents, and it's going to occur at room temperature, normal temperature. Otherwise, aldehyde gets converted, the carboxylic acid gets converted to aldehyde. So at low temperature, let me write it here. At low temperature, RCOOH gets converted to RCHO. Here you require 3 equivalent low temperature. So basically, depending upon the quantity of DIBALH and the temperature, the products obtained are different. So that's the main point to note here. Let us look at the mechanism for 2-3 reactions that will give an idea how exactly the action of DIBALH takes place in reduction reaction. Suppose we have aldehyde. It should convert aldehyde to alcohol. Say this is our aldehyde H. So first thing is to interact, because it's electrophilic in nature. So this is diisobutyl aluminum hydride. So this will actually interact with the lone pair, and it forms tetrahedral intermediate. So this tetrahedral intermediate is stable only at low temperature. That's the main reason why this reaction, wherever there is a involvement of only one equivalent of this is a DIBALH. This is a tetrahedral intermediate. It will carry negative charge on aluminum now and positive charge on oxygen. So this negative charge on aluminum actually can trigger this migration of hydrogen from aluminum to carbon. This carbon is electrophilic. So this reaction now result in shifting of this bond also. So it will essentially be forming O hydrogen. This extra hydrogen, whatever is there now, is going to be from DIBALH. So this was that hydrogen. So now this is going to be forming Al. So this on acid workup or normal water hydrolysis will result in OH. This hydrogen is from lithium aluminum hydride plus Al OH. So this will further undergo hydrolysis actually, but here we are focused on only getting alcohol from aldehyde. So this occurs at a low temperature only one equivalent of DIBALH is used, and it's a low temperature. Low temperature means minus 70 to 78 degrees Celsius. Room temperature means around 60 to 80 degrees. Slightly higher temperature means 110 degrees. These are some of the temperatures which are used for the reaction of DIBALH. The next mechanism which we are going to see is for ester. So this reagent is very convenient for ester also. IBU twice H. So basically this lone pair should attack aluminium, and that should form O plus. There is OR here also, and there is a bond now, ALH, and here you have IBU twice. Now this aluminum carries negative charge now, so as a consequence this hydrogen can attack electrophilic site, and this carbon will be electrophilic site. So it will have O, Al, IBU twice, and here now new H has come, which is from aluminum hydride, lithium DIBALH. It's from DIBALH. And once you have this hydrogen, now next we see that the reaction takes this type of pathway, because it is only one equivalent and we have low temperature. So this bond collapses back here, and there is OR here, and there is one H, which is actually from lithium aluminum hydride. So in terms of water, it's just a bond formation, and this will actually be pushed out, the leaving group H double bond O plus Al OR IBU. So this will further undergo hydrolysis, but we are not discussing that hydrolysis part here. We have got only aldehyde here. It's important. So from ester we have got aldehyde. So this is using one equivalent. Similarly, this aldehyde further can react with second equivalent of DIBALH to give alcohol also. That is not of our interest here. So we are not considering that reaction. So basically, we are able to see here that depending upon number of equivalents and temperature, it will show different reaction. So next, let us take up few examples which illustrate the reaction of DIBALH. So in first question, let us take the reaction of, so COX it is, it can be COCl also. So I have two reactions here. First one is one equivalent of DIBALH and minus 78 degrees Celsius. Second case is two equivalent room temperature. So maybe 80 degrees Celsius. 80 degrees Celsius. So this is one question. Second question which we will take up is this is furan. This is actually 1, 2, 3, 4. 3, 4 dicyanofuran. Two equivalent of DIBALH. Low temperature. So these are the two questions which can be solved, which are very interesting also. Let us look at the products here. The one equivalent is being used. So the product here should be essentially CHO, and it should be COX, because they should not get affected. So here just to give you a hint on the mechanism. This, when it reacts with diisobutyl aluminum hydride, so it's ALH, IBU twice. So this lone pair attacks actually the aluminum. So that will actually form RC double bond, triple bond N plus ALH. I would write IBU here. So you get this reaction. So here there is a shifting of bond from here to here, and this hydride will attack carbon. So it will form RCH double bond N AL IBU twice. So this is the intermediate which is formed in this mechanism actually, this pathway, when you use one equivalent. Now instead of using one equivalent, if you use one more equivalent, additional DIBALH, then there is now this nitrogen has a lone pair, so it can actually react with one more pair of diisobutyl aluminum hydride, one more molecule of diisobutyl aluminum hydride, and form something like one more equivalent. If we have RCHHN, so this will have two bonds now, ALIBU twice, ALIBU twice. So this on hydrolysis will actually yield RCH2 NH2. So this is how, when we use two equivalent, we get amine, and when we use only one equivalent, this is the intermediate product formed, and this will be the intermediate, and we hydrolyze here. So if you hydrolyze here, you get actually RCHO. So that's the important difference when we use one equivalent and two equivalent. Similarly, here in this reaction, we have used two equivalent, but there are two CN groups at low temperature also. So in that case, so here temperature also should be written as 80 degrees Celsius, because still here we have actually written mechanism for low temperature. So low temperature means this will go in this pathway. High temperature means, and high temperature, and you should have extra one equivalent of DIBALH also. In that case, we form this this product. So here there is only two equivalent of DIBALH and low temperature, so it is expected to form only CHO, CH. So this will be the product. So this is how DIBALH acts in reduction reactions. So thank you for this video, and let us meet in upcoming videos. Thank you.